First related rate problem here. This is problem 11 on page 194. The radius of a circle is increasing at a rate of 4 centimeters per minute. Find the rate of change of the area of the circle when the radius is equal to A, 8 centimeters, and B, 32 centimeters. Okay, so the first thing we always want to do when we're doing a related rate problem is first let's think about the geometry that we're looking at here, because that's going to be the equation that we're going to have to utilize. So in this case, we're talking about the rate of change of area of a circle, which tells me that we're going to need to write an area formula. So I'm going to insert an equation here, and I'm going to redo that because normally when I write equations, I like to blow them up a little bit. Equation A, capital A for area, equals symbol, here we go, pi r squared is the equation for area of a circle. Next thing we want to do here is we want to take note of any of the numbers that are given in the equation and try and give them a label. So the first one that jumps out to me is the radius of the circle is increasing at a rate of 4 centimeters per minute. So again, we're going to use the equation function. You don't really have to for this. 4 centimeters, we're going to do an equation here. We're going to type 4 centimeters per minute. And we're going to have to give that a name. The fact that it is the radius, okay, is changing, and it's changing as minutes go by, and minutes are units of time. So we're going to give that a rate of change notation, just like we would a slope or something in miles per hour when we were doing an algebra equation. In this case, we've got centimeters per minute, and that is going to be a rate of change of radius over a change in time. So we're going to label that 4 centimeters per minute as dr dt. Next, we're going to look at the other values that are here, this 8 centimeters and 32 centimeters. And what I want to point out to you about those is that those are changing dimensions. Let me go ahead and shrink that down so that fits where we're at here. Those are changing dimensions. This circle is getting larger. So the radius isn't always 8 centimeters. It's not always 32. It starts, we don't know where it starts, but it's constantly changing as time goes by. So it's important that we notice in a related rate problem which dimensions are constant throughout the problem and which dimensions are changing. And in this case, radius is a changing dimension, and that's going to mean that we can't plug that value in immediately. And we're just going to type it 32 centimeters, and we'll shrink it down so it all fits on the same line. So we've got all our information on the same line here. Boom, there we go. So we've got our equation of our circle, we've got our rate of change of the radius, and we've got our dimensions, and we noted that they're changing dimensions. Okay? Next thing we want to know is, what are we trying to find? So we go back to the problem and we read it. And it says, find the rate of change of area of the circle. So we're trying to find rate of change of area of the circle, and we want to give that some kind of calculus value. So going here to new equation again, rate of change of area, if we were to note that as a calculus rate of change notation, we're going to call that dA over dt. And that's what we're looking to find. Put a equals question mark there. All right, so let's start here. New equation. We're going to want to find the derivative I'll use the square brackets, of our area equation. Area equals pi r squared. Okay. Now, one of the things we learned in the last section was how to do an implicit derivative. That was when we had x's and y's in the same equation. And if we were taking an x derivative, that's what we've been doing since the beginning of the year. And if we started with an x squared, we ended up with a 2x. But if we're taking a y derivative, we're taking the derivative of a y value with respect to x, our y squared would become 2y times dy dx. Okay, we're going to do the same thing here. We're doing a derivative of the t value, time. Time is what's controlling the action here. This radius gets bigger as time goes by. So any variable in the problem that isn't a t, a time, is going to get that rate of change notation written with it. So when we take the derivative of area with respect to time, we're going to get, let's go ahead and new equation here. We're going to get a fraction. We're going to get dA over dt equals. Now we're going to take the derivative of pi r squared. Now keep in mind, pi is just a constant coefficient, so it's not really going to affect doing the derivative here. So we're going to end up with 2 pi r, and we're going to end up with a dr over dt rate notation. And there's our derivative. Now at this point, we stop and look at what we have here. dA dt is what we're looking for. We've been given a dr dt value to plug in. We've been given radius to plug in. Pi and 2 are just constants. So we're going to go ahead and we're going to plug in our values. So let's go up here to new equation, fraction. Okay, when I plug this in, remember, we're looking for dA over dt is equal to 2 times pi. A lot of people like to swap pi out for 3.14. That's not necessary. We can leave pi in our answer. It's the more exact way to do it. Our radius that we're plugging in is 8 centimeters. So we're going to do times 8 centimeters times, and we're going to plug in our dr dt value. And I'm going to do it as a fraction. And I'm doing this for a very specific reason. It's very important when we do this, 4 centimeters. It's very important when we do this that we keep our units correct, so that when we get to the end, and we're going to double check it at the end, but we want to get to the end, we want to make sure that we have our units correct. Okay, so we can do this math very quickly here. 2 times 8 is 16, and 16 times 4 is 64. So we will hit enter, new equation, fraction. I know this takes a little bit of time to do. dA dt equals 2 times 8 is 16. 16 times 4 is 64. So we're going to have 64 pi. And now let's take a look at our units here. We've got 8 centimeters times 4 centimeters. That's going to give us centimeters squared. And our denominator is still units of minutes. So we've got a solution here of 64 pi centimeters squared per minute. And that makes sense to us because we're looking at a rate of change of area. When we had a rate of change of radius, radius is a linear dimension. So we had 4 centimeters per minute. Now we're looking at a rate of change of area. Area is a square unit, so we need to have square dimensions on this. So one of the things I like to do is I like to plug in the units with my values so that I remember 8 centimeters times 4 centimeters gives me centimeters squared per minute to get the final answer. Now they gave us a part A and a part B, but part B is really no different. We're simply plugging in different values, larger values in that case. So we'll hit enter, new equation. For part B, we're going to get, and I always forget, start with a fraction, dA over dt equals, in this case, 2 times pi times, now instead of 8 centimeters, we have 32 centimeters. I don't want to leave there yet, times, and back to the fraction. We're still using, it's still the same rate of change of radius, so 4 centimeters per minute. And we can do that math. 2 times 32 is 64, and 64 times 4 gives us 256 pi. So we'll just go ahead and hit equals 256 pi, and that is centimeters squared per minute. And that is one of the most basic related rate problems we can do. It's a simple equation because it only has one variable in it with the r squared. Later on, we get to some more complicated shapes. We might have multiple variables in there. We might have product rules that we could do in there. Most cases, there's a way to simplify and get rid of a variable before you do the derivative so that you can avoid product rules, but not always. Can't promise that'll always happen. So there's first example of a related rate problem, number 11 on page 194, and I'll share this document with you and this video with you as well. Thanks for listening.